Well, that's odd. Good morning. Happy Friday, or Thursday. Well, it's our Friday, sort of. Let's see, I've got up on Canvas, I've got all the videos up through yesterday and the example problems that we're going to be working on for several days now. So kind of caught up there. I wanted to track down an Excel file I've got. I wanted to show you some stuff in. Thank you. Okay, well, we can get going on this stuff. There's one of the questions on the homework that asks about relativistic momentum and kinetic energy. And I can just kind of write down the formulas for them, and we'll do a few problems with relativistic momentum today. And then I think we may drop back to some of the ones we were doing yesterday with the Lorentzian transformations, because I don't think we did quite enough of those, although we could do those on Monday too. Anyway, let's see, switch to the visualizer. That should work. Got the fan cranked up to high speed in my room here. Okay, so for relativistic ordinary momentum, we would have that P is equal to mv. And here we're going to just be doing one-dimensional momentum. We're not going to try to mix two-dimensional momentum in, although there's a very interesting example with two-dimensional momentum, and I think I mentioned it, the Compton scattering. And in that, a high energy photon comes in. Actually, this isn't so much a relativistic thing as a confirmation of Einstein's photoelectric or photon hypothesis. So an X-ray photon comes in, and there's an atom sitting here that's got a little electron, and it would be part of the atom. But the photon comes in and collides with the atom or the electron. It's got so much more energy than the binding energy of the electron that for the purposes of this situation, the electron can be thought of as a free particle. It might take a few electron volts to liberate the electron from the atom, but the energy of the photon that's coming in is tens of thousands of electron volts in energy. So anyway, the electron gets knocked out of the atom, and it's taking off here in one direction. The photon is scattered in another direction with a different energy because it had to lose some to give it up there. And when this was studied, momentum was conserved. The initial momentum of the photon coming in is equal to the momentum in this direction of the electron plus the momentum of the photon in this direction after the collision, the momentum of the electron going that way is exactly equal to the momentum of the photon going this way. And so there's conservation of momentum in 2 dimensions for this situation. And this was the final proof. It wasn't really needed at this point, but the final proof that Einstein's photon hypothesis was correct, that light could be treated as a particle at times, although it's a particle that also has a wavelength, so it had both. But to the relativistic momentum, here's our classical expression for momentum. The relativistic expression looks a lot like it, except it's got a gamma in it. And so that's the difference. And gamma is, of course, our favorite buddy here. I'm just gonna use with beta equaling V over C, all right, gamma as 1 over the square root of 1 minus beta squared. And as the speed gets closer and closer to the speed of light, this thing blows up. And that means the momentum blows up. And this is something that's been confirmed in particle accelerators again and again. In particle accelerators, they can get the speed of an electron 999 ... You can get up to about 7 nines, although I think, well, I don't know that they're actually accelerating electrons at the Large Hadron Collider. They have bigger fish to fry there, but in other particle accelerations, they've got 9 nines strung together, and they'll accelerate the electrons up to speeds like that. And when that's the case, a single electron will have, well, it's got a relativistic amount of momentum, and it behaves completely differently from with that much momentum from what the classical expression would predict. And so there would be something that happens with that. And let me switch over and show you let's see, where's that spreadsheet? There it is. We'll do a new share here, the Excel file. And this is just a page where I calculated the data on, but here's maybe a better curve of gamma on this thing. The relativistic correction factor. You can see that for a long time, gamma is just close to 1, and so it's not going to make much of a difference, even up to 20% of the speed of light. But when you get up to 30% of the speed of light, you can start to see a difference, and then the difference just gets bigger and bigger from there, until when you start 0.9 times the speed of light, it's up here more than 2. And then every time you add another 9, it goes up by a factor of 3 or more. And so it takes off through the roof. So that's what gamma does. As far as the momentum goes, because it's pretty much dependent on gamma after a while, it also goes up through the roof. And so this is stuff that's been confirmed. I'll sometimes hear people that actually don't know what they're talking about, but they'll talk about how Einstein's special theory of relativity is still controversial. And I'm trying to think who it's controversial for. It's like at particle accelerators, the theory of relativity is like as controversial as the theory of wrenches, where if you have a longer wrench, you can get more torque. Okay, that's not something that's in any doubt, and special relativity isn't in any doubt either. So it's just a tool that we use. General relativity, they keep looking for disagreements between it and theory. not because it's so much incorrect, but it's considered incomplete. But the variations are going to be so far out on the edges of what we can measure that it may be a long time before we find any disagreement there. Okay, I've got another tab on here for kinetic energy, and I'm going to switch back to the IPVO thing to show you the expression for relativistic kinetic energy. And we're not going to derive these things. We're just going to accept them as they are and see what we can do with calculations for them. But as far as kinetic energy goes, well, we'll just have a little topic here for energy. There's one energy that we might call rest energy, and that's the energy that something has just because it exists. And that's where the famous E equals mc squared comes in. And that is a particle at rest just because it has mass will have that. And there are situations where this will show up. For instance, let's see, positron emission tomography, a PET scan. This is a medical diagnostic technique, and it's in some ways it's similar to a CAT scan, which is computer-assisted tomography, where with that they basically take an X-ray machine and spin it around your body. Well, it's fortunate they're spinning the X-ray machine and not your body, because they spin it around and keep taking pictures of your body with the X-rays that are slices, and then they displace the X-ray machine slightly in one direction, so they get a different slice and a different slice and a different slice, and they can make a three-dimensional map of what it is that they're looking at and do that. A PET scan is a bit different, but it's tomography, which just means mapping. But what they do is they'll find an isotope, and what they frequently do is make hemoglobin that is loaded up with isotopes that decay by positron decay. And positron decay is what happens when within the nucleus a proton decays to a neutron plus a positron plus a neutrino. And isotopes that are proton rich, and that is they have, they're kind of neutron poor is what they happen to be, but this type of decay can go on in there. This will be ejected from the atom, and it will soon meet up with an electron. This is a positron, which is just a negative electron. In fact, you could write it as an E plus if you wanted to. But the positron will meet up with an electron because the world is full of electrons. Positrons are actually relatively rare. And the positron will meet up with an electron, and you'll have this annihilation event and a little explosion there. And coming out of the annihilation event are two photons heading in opposite directions. Oh, by the way, the positron has exactly the same mass as the electron. So before this annihilation event, you've got a thing here with a particle, the mass of an electron, because it is an electron. And then you've got its antiparticle, which has the exact same mass, but it has an opposite charge. And when particle meets antiparticle, they annihilate. It's particle-antiparticle annihilation. And each of the photons that comes out of here has an energy equal to the mass of an electron times c squared. And in positron emission tomography, the detector that they have in there is tuned to look for gamma rays of this particular energy. They're actually gamma rays, which are ordinarily very harmful, but they don't put that much of this stuff into you. They put stuff in that has relatively short half-lives, so it's not in your body. And typically the risk to you of being exposed to these gamma rays is small compared to the risk of having whatever condition it is you have undiagnosed. And they use it for looking at things like cancer, for things like cancer. Cancer cells are hemoglobin hogs. You can think of them that way. They pull in a lot of hemoglobin out of your body. And so they'll inject this radioactive dye into you that's within the hemoglobin cells, and the cancer cells will draw in that at a higher proportion than ordinary cells, and so they can find out where the cancer cells happen to be in your body. They'll also use it for diagnosing heart disease. If your heart is diseased, the parts that are diseased will not draw in hemoglobin as well as the healthy parts. And so in that case, they see places that are not pulling in hemoglobin in the heart muscle and can figure out some problems there. And but anyway, this is using relativistic energy, this famous equation there. Well, that's the rest energy. What about when something is moving at a high speed? Well, there's total energy as well. And the total energy happens to be gamma times mc squared. And so that total energy can grow without limit because gamma can increase without limit as you get close to the speed of light. Well, the difference between the total energy and the rest energy is the kinetic energy. And the kinetic energy is equal to gamma minus 1 times mc squared. And so that will also increase without limit by the time you get up to, oh, let's see, I don't know, 80% the speed of light or something like that. Gamma is bigger than 1 or bigger than 2 actually. And so it can take off after a while. Some of the problems we're going to look at, the gamma factor will be so large that we won't distinguish between the total energy and the kinetic energy. And in a lot of problems, they don't say, they'll just say the energy of a particle is such and such. And in that case, you need to look at it. And for one thing, if it's not that high a speed, it's a poorly stated problem because they should specify whether it's the total energy or the kinetic energy that's equal to that. But after a while, it doesn't matter. If your gamma factor is 900 or something like that, there's not that much difference between 900 and 899. And so you won't be that far off. But that's what happens with the relativistic energy and then the momentum there. And we'll do some problems that explore this. There's one that we'll do next week sometime, that there are cosmic ray protons that come into the atmosphere. A cosmic ray is a high energy particle that comes from space. We don't know what it is that might accelerate them to such high energies, but one of the hypotheses is supernova explosions might do that. But they come in from space, and there's one that cosmic ray protons that have about the energy of a baseball going at 50 miles an hour. Now, that's not exactly a fastball, but a baseball has a mass of 143 grams or 0.143 kilograms, and a proton has a rest mass or a mass of 1.67 times 10 to the minus 27th grams. And so there's a bit of a difference there, but this individual proton will have as much energy as that baseball if it was going 50 miles an hour. And that's just crazy huge. And so, we'll talk about how those things are detected or why they think that happens to be the case. So it's a neat example. And in that case, we're going to figure out the difference in speed between that cosmic ray proton and the speed of light, because it's easier to figure out that difference than it is the actual speed. We don't have enough significant figures to give us the actual speed. So that'll be probably using another series expansion, but in a somewhat different way. So kind of a fun problem anyway. Okay, well, let's see. Let's start off with one where we might get to use a series expansion. We have a baseball traveling with a speed of 43.0 meters per second. Okay, that's over 90 miles an hour. And this is actually, I think it's still in the 90s if it's going that fast. So this would be a really good fastball. By what fraction does its relativistic momentum differ from its classical value? Well, relativistic momentum is gamma mv. The classical momentum is just plain mv. So gamma mv minus mv divided by the correct momentum, I guess, gamma mv. So we can say that. Well, looks like we can simplify that expression, I think. How about, let's see, gamma minus 1 over gamma, which is equal to 1 minus 1 over gamma, which is equal to 1 minus, gamma is 1 over the square root of that stuff. So it'll just be the square root of 1 minus beta squared. So we get to do a series expansion on this thing. And we're doing the series expansion on this. So do it yet again. That would be 1 minus beta squared to the 1/2. And our series expansion is 1 plus x to the n is equal to, oh, I can't remember it. Let's see. Oh, I think it's on our formula sheet for this class. Probably. Yes, it is. Good. I think this is the last page of our formula sheet, but right up here is the x there. So 1 plus x to the n, 1 plus nx, that's probably all we're going to use here because we've got a really tiny one, but we could also have the third term, n times n minus 1 times x squared divided by 2, which is what 2 factorial happens to be. Okay, good. That saved my neck. All right, well, in this case, you've seen me do this before, but and actually see if you can figure it out yourself. We're going to have n, that's the power that's on that thing. It'll be 1/2. Instead of x, we're going to have minus beta squared. And so what do we get? We'll have 1, that's the first term in the series, plus n, which is 1/2, times x, which is minus beta squared, plus, we're probably not going to need this next term, but we can see, n times n minus 1, that'll be 1/2 times 1/2 minus 1, which is 1/2 minus 1 is minus 1/2. And then on the bottom, we've got 2 for that one. And we're probably not going to even use this term, but we'll have x squared, which is going to be minus beta squared. So altogether, this series is going to look like 1 minus 1/2 beta squared minus 1/8 beta to the 4th. Okay, and then we can put a dot, dot, dot here because there's more terms in the series, but it's not going to be going very far, or there's no need to go very far. And in our case, our beta value is going to be 43.0 meters per second divided by 3.00 times 10 to the 8th meters per second, to 3 significant figures. And I guess we do have 3 sig figs. Let's see, 1.43 times 10 to the minus 7th. Okay, well, imagine squaring that. Okay, you're going to get something that'll, it's going to be around 2, actually, a smidgen over 2 times 10 to the minus 14th. So that'll be this one. So this term will be about 1 times 10 to the minus 14th. Okay, if you square that, you'll get 4 times 10 to the minus 28th. Okay, this term is going to be 14 orders of magnitude smaller than this term. So we can ignore that one. And again, we can approximate the square root of 1 minus beta squared with 1 minus 1/2 beta squared. So our fractional difference here ends up being our gamma mv minus mv over gamma mv is just going to be 1 minus 1/2 beta squared, which ends up being 1/2 beta squared. And this will be the fractional difference there. Let's see, 1.43 times 10 to the minus 7th squared. Okay, I've got that there. I can square it and divide by 2. And I get about, the fractional difference ends up being just 1.03, not that 3 sig figs makes a whole lot of difference, times 10 to the minus 14th. And so that's the fractional difference between the thing. And so we can ignore relativistic effects even for the fastest of baseball pitches. It's just not going to make much difference. And you can ignore it for a lot more than that. However, what if we have an electron accelerated across a potential difference of 50,000 volts? That's going to be a big deal. Excuse me. It's going to have an energy then, the electron will, of 50,000 electron volts. We'll have to do a little unit conversion here. But the kinetic energy is going to be 50,000 electron volts. And I'll have to convert that to, maybe. I may leave it at that for the time being. Can we come up with something that relates kinetic energy to momentum? Because that's what we're studying here. And we're interested in how its relativistic momentum differs from its classical value. I'm trying to think. Well, we'll see. Anyway, the momentum is going to be gamma mv maybe we can. Let's see, maybe we don't have to. We can treat that as its kinetic energy. Maybe we'll mix that in here. Gamma minus 1 times mc squared is going to equal 50,000 electron volts. This is maybe as good a time as any to introduce you to some relativistic things. The rest energy of an electron. Okay, well that's going to be mc squared, the mass of an electron, times c squared. And so we can multiply that by, take the electron mass, which is 9.11 times 10 to the minus 31 kilograms, and multiply that by speed of light squared. And we'll just do this to 3 sig figs here. 3 times 10 to the 8th meters per second squared. And we'll get a number in joules here, but I'm going to convert it into electron volts, or maybe mega electron volts. And we'll see what that comes out to. 9.11. Okay, and I get about 8.20 times 10 to the minus 14th joules. But if I multiply that by 1 electron volt over 1.60 times 10 to the minus 19th joules, we should get, let's see, well, we'll find out what we get. I get something that's not quite right, but the difference is in the third digit here. I get about 5.1 times 10 to the 5th electron volts. Actually 5.12 is what I get, and I think the 2 should actually be a 1, and that's probably if I'd included more digits on this and this, I would have done that. It's round off error, but anyway, that's about what we get. This is 510,000 or 512,000 electron volts, or it's often written as 0.51 MeV, mega electron volts. But that's the rest energy of the electron. Well, in this case, it's got a kinetic energy of 50,000 electron volts. So from that, I could kind of estimate, and actually that's only one significant figure, I guess. So we can see what the value of gamma happens to be in this case. And actually that won't be too bad. So gamma minus 1 times this thing, the 5.1, I'll just call it 5.1 because we don't have that many sig figs, times 10 to the 5th electron volts is going to equal 50,000 electron volts. And gamma minus 1, this is 5 times 10 to the minus 4th, so, or 10 to the plus 4th. EV, and I get about 1/10. So what I get is that gamma is going to equal about 1.1. and that's a dimensionless quantity. So there's going to be a 10% difference because the classical momentum is just mv, and the relativistic in this case is going to be 1.1 mv. And so this is only 10% higher, or 1/10 higher. So that's the fraction the relativistic momentum differs from its classical value. And I introduced a couple of new things on here just out of laziness as much as anything, but it's going to be handy to express the rest energy in electron volts at times. When I was in graduate school, the research I did was in nuclear physics, and when we talked about the mass of a proton or a neutron, I don't remember them exactly anymore, but the proton mass, we expressed in units of MeV over c squared, or the neutron mass. So MeV over c squared is what we used it in, and it's about 939 approximately. So MeV over c squared is a unit of mass, because if you look at the E equals mc squared thing, if you divide the energy of something by the speed of light squared, you do get units of mass, but they're somewhat unusual units of mass, not the ones that we're usually used to or accustomed to. But that's something that works perfectly fine. So kind of neat to deal with things like that. Okay, we'll save that. See if we can find another problem on here to do. And we can see, when are things going to differ from the classical and relativistic expressions? When will they disagree by 1%, and when will they disagree by 10%? Well, in other words, since the relativistic expression is gamma mv, we're really asking, when does gamma equal 1.01, and when does gamma equal 1.10? Well, we just did an example where it disagreed by 1.10, but we never bothered to figure out what the speed of the electron was, I don't think. In fact, did the question even ask that? No, it just asked for the difference. So now we can figure out what the speed of the electron will be at a 10% difference. So that's what gamma is going to be. Well, this will be easiest to do if I go through something here. Gamma, and I went through this the other day, but that's okay. It doesn't hurt to repeat. Gamma is that. We want to know what beta is when gamma is 1.01. And maybe we could use if we thought there were a bunch of sig figs after this one, we could use some kind of a series approximation for it. But first thing I'd do is rewrite this as 1 over gamma is going to equal the square root of 1 minus beta squared. And then square both sides. 1 minus beta squared will equal 1 over gamma squared. And beta squared will equal 1 minus 1 over gamma squared, or beta is going to equal the square root of 1 minus 1 over gamma squared. So in this case, we can just plug in the numbers. They're not that extreme. So the square root of 1 minus 1 over 1.01 squared. Our calculators should have enough significant figures on them that we can do this. And then remember that beta is equal to V over C. So then V is just going to equal C times beta. So we'll get this. Turn on calculator first and clear it. Second, square root of 1 minus 1 divided by 1.01 squared. Actually get, oh, let's see, 0.14. So that's about 14% of the speed of light, actually, which is kind of significant, I guess. So if I take that and multiply it by 3.00 times 10 to the 8th meters per second, we can do this in our heads, times 0.14. 3 times 0.14 is going to be 0.42 times 10 to the 8th, which is 4.2 times 10 to the 7th. Although I'm going to check that. Yeah, 4.2 times 10 to the 7th meters per second. So that's the speed where you're going to have a 1% difference between the, or error in the momentum. That's pretty darn fast for ordinary things, but for little particles, you can get them going that fast. And in fact, in that 50,000 volt acceleration that we accelerated an electron across that potential difference, we got up to a gamma equal to 1.1. And so let's figure out the speed for that one. In that case, beta will equal the square root of 1 minus 1 over 1.10 squared. And it'll be different. It'll probably be easiest just to do a new square root. 1 minus 1 divided by 1.1 squared. And I get 0.42 for that one. So in that case, V is going to be 3.00 times 10 to the 8th meters per second times 0.42, which is more. Let's see. Anyway, 3e8 times that answer. 1.25 times 10 to the 8th meters per second. And so that's a lot more. Yeah, that's almost, well, it's more than a third the speed of light. So pretty good anyway. So we're starting to experiment with some very extreme numbers, I guess. 50,000 volts, though, isn't that much. I think, I can't remember if in the old TV sets, I think I have that as a later problem on here somewhere. Maybe not in this set, but one we can look at next week. The old TV sets had a 25,000, they had an electron gun in them, is what they had. And these are the deep TV sets that had the picture tube that extended way out behind the thing. And the reason it did was because there was an electron gun in that, and they had a warning high voltage sticker on the outside of it. And the way that they maintained the high voltage was to keep a capacitor charged up to that potential difference. And so when you turned on the TV set, you didn't have to wait for that capacitor to recharge, because it would take a while to charge something up to that much. And then the electrons would be accelerated across this 25,000 volt potential difference. And we'll look at that as a problem next week, but we kind of know how to do it here. with the rest energy of the electron being 0.511 or 5 times 10 to the 5th electron volts. And then we'd have a 25,000 volt difference instead. I think it'd probably end up being 1.05. So the speed is going to be somewhere between these two, 4.2 times 10 to the 7th and 1.25 times 10 to the 8th. And you could do that if you want to figure out how fast those electrons would have been going. But they will be relativistic speeds. And when they're going that fast, if you want to finally aim that electron beam, you're going to have to build some corrections into it for the relativistic speeds that they have, the momentum and the kinetic energy. Turns out they're not easy to deflect when they're going at relativistic speeds. And so different things show up. Let's see, I'm going to see if I can, for a last problem today, if I can find another one of those ones from yesterday that we were working on. But I don't remember where I put them. And those are all the physics other class. Or maybe we can just try another one of these. We'll see how hard they are, how hard the next one is. This might be harder to find. Okay, this looks like just a little algebra problem, I think. Show that the speed of an object having a momentum of p and a mass m is that. Well, the momentum p is equal to gamma mv, and gamma is equal to, so I'll have mv on top, and on the bottom I'll have the square root of 1 minus v squared over c squared. So looks like I'm just going to be rearranging stuff here. So let's square both sides of this. P squared will equal m squared v squared over 1 minus v squared over c squared. I'm trying to think what use this expression might be up here, but I guess if you happen to know the relativistic momentum of something, it might be useful. Multiply out from underneath by that, and I'll get p squared minus p squared v squared over c squared is equal to m squared v squared. And then kick this across. P squared will equal p squared v squared over c squared plus m squared v squared, which is v squared times p squared over c squared plus m squared. What am I solving for here? V. Okay, so I'll divide by that. V squared will equal p squared over but P is gamma mv. We'll have to see. I don't actually, or maybe I want P's in this. If I multiply top and bottom of this by P, or 1 over P squared, I will get on top, I'll get 1 divided by C squared plus M squared over, oops, that's a 1 over C squared, M squared over P squared. And if I multiply top and bottom by C squared, I'll get c squared on top over 1 plus m squared c squared over p squared. That looks like mc over p. Yep, this is how you do it. And then you take the square root of each side. So v will equal, the square root of the top is just c, square root of the bottom is 1 plus mc over p quantity squared. So that works. And I could do one more step and rewrite that. So that's just algebra, is playing with that. That'd be a good problem for a maybe Math 99 course where they have to solve an expression for something different. Although it might be too hard for that class. I used to teach that, and I don't think many students would have had success with that. Okay, I think the homework that I assigned is, you should know how to do everything on there now, especially now that you can answer that question about relativistic momentum and kinetic energy. But I'll probably post the next homework assignment, which is going to include things like the Lorentzian transformations, and then we'll have questions on relativistic momentum and energy in there. And the relativistic momentum, we can start looking at things like collisions between things where particles are going at relativistic speeds, or we can look at radioactive decay where a particle may come out of a nucleus with a relativistic speed. And so we can figure out the recoil speed of the nucleus that's left behind. And so things like that can be kind of interesting to mess around with. But those are the things that physicists have been dealing with since they started studying elementary particles and radioactive decays and things like that. So this is sort of out there. The relativity stuff may be useless to you. In most fields, you don't have to think about it much, but it's just nice to stretch your brain on it. And maybe some of the math, the series expansions might be useful for you, I hope. So see how that goes. And otherwise, good weekend.